Kirchhoff's laws are two rules that, when used in combination, allow us to analyze complicated circuits piece by piece in a structured and simple way. Let's gain an intuitive understanding of these rules, starting with Kirchhoff's voltage law. Imagine a channel of water running from the top of a hill, with its elevation dropping progressively as it flows over a number of water mills to the foot of the hill before being pumped back to the top and recirculated. It makes sense to say that for every decrease in elevation along the path of the water, there must be a corresponding increase. That is, if we were to traverse the waterway from any point, we would end up at the same elevation we started at. This is directly analogous to an electrical circuit. The decreases in elevation across the water mills represent the drops in voltage across our complex impedances, and the pump represents the voltage source. From this observation, we develop an understanding that for any complete loop, every drop in potential must have a corresponding increase in potential. Therefore, the sum of the potential change about the circuit, some negative, some positive, must sum to zero. Here, if we were to consider a circuit with an unknown voltage source and three loads with drops of 2 volt, 3 volt, and 5 volt respectively, according to Kirchhoff's voltage law, the source must be 10 volts. We'll now look at Kirchhoff's current law. Picture a water channel splitting into 3 smaller channels. If we make the assumption that no water is seeping into the ground or otherwise escaping the confines of the course, we can see that no flow is lost across the area of divergence. This is directly analogous to our circuit, with the multiple channels representing multiple wires meeting at a node, just like this area of convergence. The water itself represents the current flowing across the node, between wires. From this intuition, we develop an understanding that at a node, that is, at any point where multiple current-carrying wires meet, all current that enters the node must exit. No current just disappears. Therefore, the arithmetic sum of the current entering and exiting must equal 0. Here, if we consider a node in a circuit consisting of a current source of known direction and unknown amperage, as well as 3 loads of current 2, 3, and 5 amps respectively running through them, according to Kirchhoff's current law, the source must be 10 amps. Note, we have assumed that current is flowing out of the node in each of these cases.